Okay, are we here? Are we? Oh, anywhere. I'm coming back. 1 minute. 1 minute. All right, I am back. All right. Good afternoon, everyone. How are you guys doing? It's good to see you here. Welcome. We're in the new channel. Parametric camp. Woo! Well, I'm very happy to see you here, and um, I hope we can start slowly transitioning into this channel and build a community around it. I will be, for the foreseeable short-term or medium-term future, I will be here for sure, but I would like to build more of a community around it. I kind of like that I'm starting to see familiar faces constantly on the chat. I see Monique, I see Chandra, Kartik, Galiaf, I see Pixel Car, Saeed, people that I keep seeing over and over. Hari Prasad is there. He's been helping me a lot. I like seeing people constantly, recurrently. I think it's like a nice thing to build community around this. Maybe at some point we find a better way to communicate and keep this conversation alive over the week, and like share files and share content. That would be great. I signed up for the Discord channel. I told you about this. I signed up for the Discord channel, but I really don't have the bandwidth right now yet to maintain it and to start. So if any of you wants to volunteer to be the community manager of the Discord and have like a forum and like with chats and stuff, you would be. I'd be more than happy to give you the power to and to lead that effort, which I do not have the time to do right now. So, but it would be great to do that. So, welcome. I'm happy to see you here. So, what we are going to do this afternoon, as I said this morning, is we're going to write a very nice algorithm. It's called the Raymer-Douglas-Peucker algorithm for polyline simplification. And actually, let me show you. As I said before, well, and then, so we're going to spend some time implementing this. It's going to take me some time because it's a very simple algorithm in a way, but we're gonna have to go over like some small topics on data manipulation, and I will want to draw a lot of diagrams so that the process that we're following is very clear. So it's gonna take me some time to wrap this, but I hope to take like an hour or an hour and a half to do it, and then perhaps we can go to Q&A and we can spend some time like talking and chatting, etc., etc. So yeah, so let me refresh what we're going to do today. Or should I start recording right away? I mean, I can probably start recording right away, right? Um, so we left this morning. We left this morning with we wrote the two algorithms for computing the distance between a line and a point, and that was going to be very important for this algorithm. So for this video, what I would want to do probably is I want to record the introduction, which I will do at the end with the thing working and show how this works. Um, and then immediately the first thing that I will do is like I will explain how the algorithm works. So I will show probably the Wikipedia page, and I'm going to show probably the diagram that is like right there at the all the way at the right. and then I'm going to draw some whiteboard diagrams to explain how we're going to follow. And I'm going to do it in a very, very stepwise manner because I really want all of us to be together while we're doing this. And I don't want to lose anyone, okay? And so, so, so yeah. So let me wrap my head around 30 seconds to think and plan this. Decaf coffee. Oh. So introduction, okay, and then I want to explain that this algorithm is also not an optimized one. It's just one that it's going to be simple to implement because I want everybody to understand what we're doing. Okay, so I think we're just gonna start, and if it doesn't work, we can just backtrack and like record the clips again. So let's just do that. Are you guys with me? Is everybody ready? You are welcome to follow while we're coding this thing. It's not going to take, the code is going to be fairly simple. It's going to be like this morning. It's going to take me some time to break down the concepts because I really want to explain the algorithm real well. And then the coding is actually not going to be that tedious. So let's get started. Let's talk a little bit more in detail about what we're going to be doing. What we're going to implement is called the Raymer-Douglas-Peucker algorithm. I hope I pronounced that well. I'm really bad with names in English. And this algorithm is a really nice algorithm that is designed for polyline simplification. It's commonly referred to as the Douglas-Peucker because I believe that historically the two authors came up with the idea simultaneously, right at the same time, but without talking to each other, and they actually got their papers published on the same journal, on the same edition, back to back, one after the other. So it's kind of unfair to attribute it one to one or the other. But it's a really simple algorithm, which is very interesting because it's a very nice way of simplifying a polyline. Because, for example, imagine a polyline and imagine that the polyline has 100 points, right? We can come up with a lot of simple rules to simplify that polyline. Like, for example, why don't we just eliminate every other vertex, right? And then we end up with roughly half of them. But the problem with such simple approaches is that, for example, if the polyline has like more of like a convoluted geometry on some edges and less density of points in others, then maybe the overall shape of the polyline with such simplification would get very distorted, and we will be keeping points that are not really adding detail to the polyline, and we will be pruning out other ones that actually contribute to the overall shape. So the nice thing about this algorithm is that it does a really good job at sort of maintaining the overall high level shape of the polyline while simplifying the points that are not really adding much detail or they're not really contributing much to the overall shape. So, and it's also fairly easy to implement. So what I mean with this overall shape, like, is in this curve that you can see here, you can see how the overall shape is basically an undulation that keeps damping down. So the algorithm is actually smart enough to be able to identify which are the vertices that actually represent the spirit of this polyline, and then keep those, as opposed to the other ones, for example, all the vertices that would be in the middle of this like almost straight line, which are not really adding much detail to the polyline. But how does this algorithm work? So it's actually very interesting because it's also a recursive algorithm, which I will explain more in detail what that means. But the process basically goes like this. We start off a polyline like this one. And then what we do, and we start off also from a distance parameter that we call the epsilon. And that distance parameter is going to be sort of the value that we use to control how defined we want the curve to be, the polyline to be. And how it works is like we start by taking the endpoints and figuring out which one is the point that is farther away from this initial straight line. And once we have that point, if that point is outside of this epsilon range. So let me show the diagram again. So you see the line, and this point is farther away from distance epsilon, then that point will be kept. However, if like we have here, if like here, if the point is inside of that epsilon distance, so if the distance of the point to that line is less than the epsilon value that we are setting, then it means that that vertex will go away from the polyline. The result of that is what you're seeing here. This polyline gets simplified. This one, and this vertex, they all go because you can see intuitively that they're not really adding much detail to the overall shape of the polyline, which I think it's a really interesting and a really smart way. Why are we going to do this? We're going to do this because polyline simplification is actually a technique that is very common and very useful in many different fields. So for example, if you're doing robotics and you send a very complex polyline for the robot to follow that has thousands of points, then the robot may actually not be able to take all of that, and simplifying it in a way that it still maintains the overall trajectory of the robot is a very useful thing to do. It's also very useful, for example, when you want to simplify diagrams that are made of tons and tons of polylines, but you want to keep the overall shape of the sketch, for example, if you're drawing, So it's a really useful technique, and also it's a very nice algorithm to implement because it's not very hard. So we're gonna see how to do that. So actually, before we start any coding whatsoever, I would like to spend some time in the whiteboard and then break down the step by step the process that we're going to follow. Okay, so let me draw some stuff and let's explain stepwise what we're going to be doing to implement this algorithm. Okay. Okay, what is it that I need to see? Up, I agree, will be very useful. Perhaps we can talk about, I don't know what you guys are talking about, but maybe we can, maybe we can, so maybe we can talk about that by the end of the stream in the Q&A, okay? So just follow up, just go back to that. Okay, so I'm going to draw a sketch for, I'm still learning how to use this thing, so forgive me if, but now I learned from this morning how to draw polylines, okay? So, okay, so I'm going to do this, and this, and this, and this, and this, and this. Oh, that's a very long polyline, sorry. Now, this one, this one, this one, this one, and this one. Okay. Nice. Much better than this morning, huh? Okay, and I'm gonna start. I'm gonna label this. I'm just gonna do this manually because otherwise it's gonna take forever. So I'm just gonna label this. This is going to be point. Oh, nope, sorry. This is going to be point 0, 1, 2, 3, 4, 5, and 6. And then, now that we have this, I'm going to use green, and I'm going to draw a line. I'm going to talk about the value of epsilon, and I'm going to draw more. Yeah, I'm going to, yeah, okay. 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 All right. So let's talk about algorithm. Whenever you design an algorithm, this is a super important thing that you need to do before writing any code. You need to sit down and sketch what you're going to do, and then go and do it. Okay. before, so you think, always think before writing any single line of code. Otherwise, your life is going to be a nightmare. I can tell you by experience. So here I just drew a polyline that has 7 vertices. Remember that in computation, we usually start counting by 0 and we end up whatever the number of vertices minus 1, okay? And then how the algorithm works is the following. The first thing that we do is we are going to draw a straight line between the first point and the last point. We always start between the 2 end points of a polyline. All right. Now that we have that, we can, I'm just going to draw this band of sorts, which is going to represent, which is going to represent, and this distance here, is going to be epsilon. Okay. What does that mean? It means that all the points that once we have chosen the first one and the last one, what we want to do is we want to calculate all the points in between, which one is the one that is the farthest away. So what we do is, for this particular case, it's very easy to see that the farthest away would be point number 3, okay? And because we see that this distance here is much larger than epsilon, which is the value that we're using for the precision of the polyline, then what we have to do is we have to follow a recursive process where what we're going to do now is we're going to subdivide our polyline in 2 chunks. Okay, so one of them is going to be the beginning of the polyline and that vertex that we just chose, and the other one is going to be the vertex that we just chose and the other end of the polyline. Okay, what does that mean? What we do now is we say, well, we're going to apply the exact same logic to those 2 independent chunks. So we're going to assume that this here is now our polyline, the one that we want to simplify, and then we're going to operate the same thing. We're going to calculate which one is the farthest away, and this one is going to be if we draw this diagram, we're going to assume, if we draw this diagram, we assume that this one is outside of epsilon, and because it's outside of epsilon, then we actually now forget about it's outside of epsilon. So now we take the polyline that we had and we subdivide it in this polyline and this polyline. Okay, and doing this, now we can see that if for this polyline we calculate the farthest point, which is obviously this one, and if this one is included in the distance epsilon, then we remove this point. So this segment now becomes a permanent segment. Now becomes a permanent segment of our final geometry. This one here. For the second one, between 2 and 3, because there's no points left in between, we're going to also include this here. And now we go back to the other one that we had on the far right. We also do the same thing. We calculate whether if any of these points, so this point here and this point here, if any of them, which one is the farthest away, and we can see that in this case is number 4. And if it just so happens that all the points, that the point that is farthest away is inside of epsilon, so if the distance of that point to the line is less than epsilon, then because it was the one that was farthest away from all the points, then we can see that that whole segment is a segment that can be simplified by removing all the vertices in that particular segment of the polyline. Because if the one that was farthest away is still less than epsilon, then all the other vertices are going to be also inside of epsilon. So what that means is that the simplification here is now very clear. I can remove this and I can say this is going to be part of my final polyline. And you can see that this is the process. You can see that this polyline that had 7 vertices, we have removed 3. So now it has 4 vertices. Let me draw like a thicker line here. 1, 2, and 3. Okay? And that's the simplification. What's interesting about this is that we have applied a recursive logic. We started with, let's simplify the whole polyline, but we found a vertex that was outside of epsilon, so we divided the polyline in 2 segments, and then we said, okay, let's now simplify the left part, and then we will simplify the right part. The left part, oh, we also had one that was outside of epsilon. Okay, so then let's subdivide that in 2 more polylines and apply simplification to each one of them, and so on and so on. So you can see how we're going to create like a tree or recursive operations until we reach a point where the polyline can be simplified and all the vertices can go, or we reach a situation where the polyline only has the start and the end points and there's no simplification to be made, in which case we don't keep going farther down. All right, that is the idea of a recursive algorithm, which is a very common technique in computer science. All right. So how about we start writing some code and make this happen, huh? Okay, was that clear? Oh, it's a little late also for me, so I don't know if I'm making a clear point here. Okay, let's switch to Grasshopper. And how are we going to do this? How are we going to do this? I'm going to create a, should I just draw a polyline and bring the polyline in? And then I'm going to do like a list of points probably. Bring a list of points. How do I want to do this? I want to make, I really want to make this very clear. So I'm just going to draw a bunch of points here. Okay. Yes, I'm just going to draw a bunch of points. Okay. Set multiple points. This one, this one. Okay. Okay, I have a list of points. Okay, and then a polyline between them. That's very clear. Okay, so I have that polyline. And then I'm also going to label them. I'm going to label them. I think that's going to be useful. Let me see. Labeling. Location of the. Okay, sorry. No. Location of the text tag. The text to display. No, there was like a something to label points, right? Text tag 3D. The text to display. I get off. Wasn't there like a vanilla component that just gave you the numbering of the points? Was this something like this? I don't know. Dot point display. Okay, dot display. You're right. Pointless. Exactly. Thank you. Thank you. I don't know what I would do without you. Okay, you're right. Okay, and then here, and then, okay, I like that. Okay, and I'm going to hide this for the time being. Okay, and then I'm going to C#. Yep, I'm going to feed in here points and then epsilon. And I think this is probably a good place to start. Do I want to draw something where I draw like the start at the end? It's okay. I think we can do this numerically. Okay, so I'm gonna start by bringing everything in, and then we need to doing a first round of calculating the distance of all points. Okay. All right. So let's get started. What you see here is that I really quickly put together a very simple polyline. So what I did was I created like a bunch of points here in Rhino, and then I brought them into Grasshopper with a parameter component. And then just for the sake of visualization, I joined them with a polyline. And then I also added this point list so that I know their indices, which will be very useful in very soon when we start debugging the code that we're going to be writing. I want to make something very clear, and I would like you to think of polylines. I would like you to think of polylines not as segments that are moving in like a saw kind of shape, but actually a polyline is nothing more and nothing less than an ordered list of points. So I actually don't care at all about lines or segments, whatever. I care about the XYZ coordinates of each one of the points that are part of this polyline. So for my C# script component, I'm actually not going to take I'm not going to take a curve, or I'm not going to take a polyline object. What I'm going to take is 0.3Ds, and I'm going to take them as lists. This is very important because I want to have a full list of all the points one after the other. Epsilon is going to be the value of type double, and I'm just going to plug in here some slider with a lot of precision, and I'm going to use this to control that distance, the distance that I was talking about before. And then I think at this point we are ready to start writing some code. And the first thing that we're going to do probably is we're going to start with the first round where we compute the distance of all these points to the first line segment that we're going to create between the start and the end points. I need to bring in code from this morning, right? Nope. Nope. Okay, so where are we? Stream. Okay. Which one are we going to take? We're going to take the cross product, for example. I find it a little more elegant. Yeah. So distance to line, we're going to simplify the name a little bit, and then here we're going to go back to vector3d.crossProduct, which is part of Rhino Common, and we're going to start off with this code. Yeah. And something that I want to do also, I want to do this as a function. I don't want to do this in the main code. So, or actually I could just keep this for the sake of the, why not? I could just keep this here. Compute distance of point to point B to line AB. Compute cross product of two vectors, for example. And then here I'm going to, yeah, why not? I mean, we had it there already anyway, so why not keep that? Okay. And then here we are going to, we're going to we're going to what are we going to do? Okay. Okay, so I'm going to start again. I'm going to jump in again by explaining that I brought this from this morning's code, and I'm going to link to the video, and then I'm going to start creating a function that is going to compute the distance of all to all the points. Okay. All right, and finds the largest one. Before we start, it's going to be very important for this algorithm that we have a way of calculating the distance of a point to the line that is formed by two other points. And I have a geometry gem that I recorded where I explain how to do this, and I wrote the algorithms. So there was probably going to pop up a link somewhere here, or you can find it in the description. But so I copy pasted some of this code. I copy pasted a function that, given a point P, computes the distance of that point to the line formed by two other points A and B. And because this implementation is using the cross product, I'm also copying here an example of how to write the cross product of two vectors. I am using C# scripting within Grasshopper, so I could access the Rhino Common API to do this. But if you're trying to write this on a different C# environment, then this implementation will be super easy to copy and paste it between different implementations. Okay. All right, so I think we're ready to start writing some code. The first thing that I would like to do is I'm going to, instead of writing everything here in the main code, because this algorithm is going to be recursive, it's very important that I write a function that takes a list of points and an epsilon value and returns a simplified list of those points, because I will be calling that function recursively on top of itself over and over. So I'm going to do that here. I'm going to create a function, and I'm going to call it simplify polyline. This function is going to take a list of point 3D objects, for example, points, and it's going to take a double value called epsilon. And the return type of this function is going to be also a list of points, because it takes a list of points but returns a simplified list of those points. And I'm going to start real quick by returning null, so that I can see that if I run this, I don't get any errors. And I'm going to write here very quick that the result of this outcome, so the result is going to be simplify all those points and the input using the epsilon value that we have as an input for this Grasshopper component. Okay, so this function is now an empty function that does absolutely nothing, and you can see here that it gives me no data whatsoever, but it also doesn't give me any errors. Okay, so we are at a good position to start writing some code here. And the first thing that I would like to write is, the first part of the algorithm is, let's take the start point, the end point, and then let's calculate the distance of each one of these values, each one of these points, to the line formed by these two vertices. Okay, so that's very simple to do. So for example, I can do that with a for loop where I say I is less than I. It's going to start with 1, okay? Because here I don't want to start. I don't want to start with. I don't because if the start point is point number 0 and the last one is point number 7, the first one that I want to check is point number 1, 2, 3, all the way up to 6. So that's why this for loop. Where did it go? Oh, okay. I don't know where that went. So I'm just gonna write it again. So I can start with a for loop that starts at the value of 1. I is going to be less than however many elements are in this polyline minus 2. So for example, I have to go from 1 to 6. There are 8 vertices in this polyline, so the last one is going to be 8 minus 2. So it's going to be points dot count minus 2, and then I plus plus. And then for each one of these, I'm going to calculate the distance, double D, the distance between that point and the start and the end point, the line formed by the start of the end point. So that's going to be distance to line, and the point that I'm going to check is points I, so each one of those points in the middle of the polyline, and then the points at the ends, A and B, are going to be points 0, the first one, and points dot length minus 1, which is going to be the last one of the polyline. So I'm going to print this to the console just to make sure that things are working correctly. And I got an error. That's very common. So number 66, yes, I use points. I use PTS, which is the value of the points on the component, but it's not the value that we see here on the function. So I'm going to replace that. And then I am using length, which is only for arrays. I should use count. And then 68 print. Okay, so I'm going to print this distance, and you can see that I have 5 distances, 1, 2, 3, 4, 5. Oh, that's not, something is not going well here. So 1, 2, 3, 4, 5, 6. Oh, because it should be less or equal than point minus. So it should be, yeah, so this is minus 1, okay? So let's see if this works. So if we have a line from 0 to 7, this point 18 units, this point is less 10 units, this point is 45, a lot very far away, 32, 36, those two are close, and 20. It kind of looks like it's working because it looks like 3 is the one that is farthest away from this line. So we are good. Okay, so that's a good start. The next thing we need to do is we need to figure out which one of these is the one that is farthest away. That is very easy to do. In this algorithm, we can keep track, outside of the for loop, we can keep track of the maximum value that we do by initializing 2 variables. I'm going to initialize a variable called maximum distance, which is going to be the variable that I'm going to use to keep track of the maximum distance that I have found over all these points. And I'm going to initialize it to a ridiculous value, like for example, minus 1. You cannot have a distance of minus 1. So because it's so small, every single value that we find distance is going to increment this. This is a very common technique to do. And I'm going to also initialize an integer, maximum index, which I'm going to use to keep track of whenever I find a point whose distance is larger to the line than any one that I have found before. I want to keep track of which one that was. Was it 0.1? Was it 0.3? 0.7? So I'm going to use this integer, maximum index, to keep track of the index of the point that I find with the maximum distance. And I'm also going to initialize it to a value that is ridiculous, minus 1. We cannot have a point on a list with an index of minus 1. That is just not possible. So because that's the case, then it will be helpful for us to identify if we have found such a point or not, etc. Right? And then here, what I'm going to do is I'm going to say double d equals the distance. And if the distance that I found for this point that I'm checking in the for loop, if this distance is greater than maximum distance, so if it's greater than any other distance that I have seen before, then to turn maximum distance into that value. So if the largest value was 25 and now I have 40, then now my largest value should be 40. So maximum distance is now the value of the distance that I just found. And then the value of maximum index is the index of the point that I am checking right now. Is that okay? Let's see if that works. I'm going to print here index, maximum index is going to be equal to I, and then maximum distance is going to be equal to max dist. And I have a typo here. This is not I, is maximum index. Let's see if this runs. I'm going to close this here, and it looks like this is working well. It looks from my polyline that number 3 is the vertex that is farthest away, and that 45 is the distance between this point and the virtual line between 0 and 7. So we're on good track, okay? -1 is possible in Python. Yeah, that's why Python sucks. I'm joking. But those are the strange things about Python that sometimes for people who come from C family of languages, it's very hard to wrap your head around. Okay, so what is the next thing that I'm going to do? So the next thing I'm going to do is there can be two scenarios between which this point is, this distance is smaller than epsilon or is not. And I think the easiest one to do is when it's not, because basically we just remove all the points in the middle. Okay, so I think I'm going to start with that. And I'm going to crank this up so that we can, if that was 45, we can do 50. Okay. Okay. What is the next thing we're going to do? If you remember from when I described the algorithm, there's two things that can happen when we find the point that is farthest away from that line between the endpoints of the polyline. If that point is inside of the value of epsilon, then if that point is outside, then we have to start subdividing the polyline and applying the same logic to the two ends of the polyline. That is a little more involved. We will do that last. But then if it's not, if that point that is farther away is the distance is less than epsilon, then that means that that point should also be removed because their distances are also going to be smaller than epsilon. Okay, so that one is a bit easier to do. So after what I wrote here, here I already know for this segment of polyline which is the point that is farthest away and how far away it is. So what I'm going to do here is I'm going to write a very simple conditional, and I'm going to say if maximum distance of this point is greater than epsilon, then here I would have to do recursion and I would have to divide the polyline and then analyze the two segments independently. Otherwise, if it's not, then what I need to points. I'm gonna write it here. Do subdivide poly and apply recursion. And then otherwise, just remove all points between endpoints and return. Okay, so let's do that. Oh, sorry, I forgot I was not. Yes, thank you. So I'm going to write a very simple conditional where I say if the maximum distance is greater than epsilon, then please subdivide the polyline and apply recursion to the two ends. But otherwise, if it's not, then just remove all the points between the start point and the end point of the polyline. Okay, so this is going to be easier, so we're going to do this here. Before I decide what to do with each one of them, I'm going to create an empty list here, which is going to be clean points, and that I'm going to not even initialize here. And what I'm going to do is here I'm going to write some placeholder text like should do subdivision here, and then here I'm going to initialize this list to just a new empty list. Just a new empty list. And here, what I'm going to do is I'm going to create I'm going to write, I'm going to say for the polyline that I had, I'm going to keep only the first point and the last point, and that is the list of clean points that I need to return. So clean points is going to be equal to a new list of point 3D objects, okay, that I can initialize, and I'm going to initialize it with 2 points. One of them is going to be the first one on the list, and the other one is going to be the last one on the list. So it's going to be points.count minus 1. And I'm not sure if you're familiar with this kind of syntax. This is C# syntax for creating a new empty list of point3D objects and then giving it some initial values. So 0.0 and the last point. Let me see if this works. This works, yes. And then what I'm going to do is I'm going to return from this function, I'm going to return the list of clean points, which either has something for the subdivision or that has this clean polyline only with the first part and the end part. So let me see if this works. So I'm going to execute this. You can see that that epsilon is right now at the value of 10, and you can see that here it says, oh, the maximum distance is 45, is greater than 10, so I should do some recursion. But if I crank this up all the way up to above 45, then what should happen is that all of a sudden I should be getting the output, which is just the first point and the last point. Let me add a polyline component here just to make sure that exactly. And because this, in a way, is the simplest form of simplifying this polyline, just the very beginning and the very end of this polyline. So this is a good beginning. So now let's see how can we split the polyline in two and then apply recursion and apply this logic to each one of the two ends. So follow me on this one. Okay, I think I'm going to change this because I think this is going to make things a bit easier to understand. Yeah. Okay. How is that going? You guys good? Is this, oh, this vertex is right on top of my head. Okay, so I can move this all the way up here. Is it better? Okay. Is this too much? Am I fast? Am I going fast? Is it clear? Am I going too slow? Can you guys take more? Okay. I'm going to save this for the sake of a Raymer, and this is going to be also Raymer. Okay, good. You good, Said? Happy to hear that, man. Okay. Okay, so I think I'm going to do some sketching. Right pace, can you please add new lines? It will be more graphical to a viewer. What do you mean new lines? I don't know what you mean with that. It like a little bit when we couldn't see the code. Okay. Galiav, what do you mean more adding more lines? You mean in the code? More lines of code? Oh, okay, yes. Bigger font size, that is great idea. Yeah, I tend to forget that. I'm sorry. Okay, and I think I want to draw stuff here. So I'm going to go back to my drawing board. Yeah, I'm going to draw a little bit here. So I'm going to add a new layer. I'm going to add a new layer. Ah, too bad. Okay. Okay. I'm just gonna make this. Okay. Nah, I guess it doesn't really make sense to do that. I'm just gonna do this. Yeah, I don't like the fact that the line is right at the middle. Ah. All right, I'm just gonna draw a new polyline here. Yeah, screw it. Okay, so I mean it takes more time to say it than to actually do it. So yeah, so something like this and this and this and this and this and this and this, for example. Okay, and takes more time to say these things than to actually do them. And then I'm going to write here. I'm going to write here. Nope. I'm going to write on a new layer. I'm going to do 0, 1, 2, 3, 4, 5, and 6. And then I'm going to draw here. I'm going to draw some lines. And then I'm going to draw here and here. Okay. Sometimes there's a mic issue. Sometimes there's a microphone issue. Well, that's not good. There's something like a duck. Maybe we can draw a duck somewhere later. Okay. So what I'm going to explain now is the thing with the indices. I want to make some emphasis on that as well. So okay. And I'm going to write here that I'm going to write here that we have here that we're gonna have 7 points. Okay. in case I need to draw stuff. Okay. So, okay. I have to do that. Ooh. uh, wait. Yeah, sorry. I'm very lonely here talking to these screens. Okay, let's get serious and let's get something going. Um, um, okay, let's get back to it. Before we go any further, I want to go back to the writing board, to the whiteboard, because I want to explain how we're going to do this. Remember that we have decided that we have found out that vertex number 2 is the one, this one here, right here. I can touch you. The one right here is the one that is farthest away from the line between vertex 0 and vertex 6, all the way up there. So what we need to do now is we need to divide the polyline in 2 parts, divide and splitting it by this one here, and then perform simplification on this one, the polyline between 0, 1, 2, and then perform simplification also on the polyline 2, 3, 4, 5, 6. Okay? Therefore, and then apply the same logic, but to those to those 2 separate polylines. And then once those have been simplified, then we will mix them together and into the simplified polyline. And in order to do that, what I would like to do is I'm going to go back to my code, and then I'm going to say here, whenever I subdivide the polyline and apply recursion, let's start by doing the following. What I'm going to do is I'm going to create, because remember, polylines are not really polylines, are just list of points. So what I need to do is I need to create a list of points that contains point number 0, number 1, and number 2. So what I'm going to do there is I'm going to say point 3D, I'm going to say left poly, okay, is going to be equal to a new list, it's going to be equal to a list that has all the vertices starting from 0 to number 2. So how does that work? I have all the points of the polyline here. So lists in C# have a property that is called getRange, and getRange gives me a certain subset of the points in that list. And the way this works is that the first parameter is the starting index of the element that I want to grab. So in this case, because we're taking the left chunk, the first one is going to be 0. And then how many elements do I want to grab? Okay. In this case, if you remember, let's say the index of the vertex that we want to pick up is vertex number 2. So if we want to start at 0 and we know that the vertex that we want to stop at is number 2, we know that we need to take 3 vertices, which means that what this means is that if I know the index of the vertex that I want to take, I want to take that vertex plus 1. So you see here, vertex number 2, I want to take 3 vertices. Starting at 0, I want to take 0, 1, and 2. So that's how we're going to that's how we're going to simplify and take the left chunk of this polyline. But now I also want to do the same and then pick up the right part of this polyline. Okay, and how are we going to do this? Well, we're going to do a similar thing. We're going to use getRange, and now we want to start with the first vertex being the one that we know is the farthest one away. So we're going to do max index, and then we need to calculate how many vertices do we need to take. And in this case, remember this polyline that I have drawn here has 7 vertices, and you can see if you count that we want to get 5 vertices We're going to take 2, 3, 4, 5, and 6. What that means is that the number of vertices that I want to take is, starting with number 2, I want to take the amount of elements that are in this polyline, in this case 7, minus the index of the vertex that I want to pick, in this case 2. Because I want to take 5, I want to take 7, the total, minus 2, the index. So that's what points dot count minus maximum index. Okay, let me check that that is correct. Is this working? It is not. Oh yeah, well, it's not working for a different reason. So here is telling me that I'm using an unassigned. So for that error to go away, I need to create at least an empty list here. But everything else is working well. Is it though? Yes. If I go down, this doesn't give me any error or like out of index, blah, blah, blah. Okay, so I have the left polyline. And now what I can do is I can actually do recursion. So divide poly in 2 parts, the left and the right. And now apply recursion to each one. So what I'm going to do is now I have a smaller polyline, the left polyline, which is just 3 vertices. So I'm going to apply that to, I'm going to apply to recursion to that polyline. And what I'm going to do is, remember I am on the simplify polyline function. So what I'm going to do is, I'm actually going to call this function again from within itself. That's exactly the concept of recursion. It is, I am on a function that is going to call itself to perform like a subset of its operation, that is going to call itself to perform another subset of the operation, etc., until we hit one of those limits that we were talking about before. So I'm going to say, I want to simplify now the left poly, and I want to use the same epsilon that I've been using before. Okay? And this function is going to give me, as a return, is going to give me a list of points that has been simplified. So I'm going to do something like this, and I'm going to say the result of that simplification, I'm going to store it in a variable that I'm going to call left simplified, for example. And I'm going to do similarly, I'm going to do the same with the right end. I'm going to say right simplified is going to be simplify polyline and right poly. Is this clear? I'm taking the 2 ends, the 2 polylines that I created, and which have less vertices, and each one of those, I'm also going to apply a simplify polyline to each one of those 2 ends. Okay? And I'm going to store those 2 results here. Whew. Recursion. Okay. How can I now keep explaining this in a way that makes any sense? Okay. I may want to go back to the diagram here and explain that for the left one, what probably will happen is that it gets simplified just because that vertex number 1 is very small. So it's going to return right here. It's going to hit this and it's going to return clean points. So I'm going to be done on this end, but on the right side, it's probably going to keep simplifying and simplifying. Simplify your thank you, Said. Simplified. Exactly. Thank you, Said. I want to do the left, so, and then the left will keep on subdividing and it will keep going. Okay. I just want to make this process very clear again. If I go back to the diagram, you can see that we have divided the polyline in two. Okay, what's going to happen probably is that now I'm calling simplify polyline on this segment, and what's very likely to happen is that number one is going to be very close to the polyline. So what that means is that when we call this function simplify polyline on the left end, we're going to start over here again, but we're probably going to end up here because the maximum distance is probably not going to be greater than epsilon. So you're going to see that this is going to immediately return a list of clean points that only contains 0 and 2. And therefore, we're done on this branch of the calculation, on this branch of the recursion. But on this branch of the recursion, there's probably going to be even more recursion going on here, because as I do this end here, you can see that probably I will end up splitting on vertex number 3, and I will have to apply recursion to this segment here and apply recursion to this segment here and simplify those two independently. So you can see how recursion starts branching down and it starts creating operations that are like atomizing the simplification until we hit a limit where there's no more possible simplification to be done. And therefore, we return a list of clean points, and then we start tracing back all of our recursions until everything starts mounting back together. So let's see, for example, let's see how can we let's keep going. Okay. I think it will be nice to see epsilon as a line. It is nice, but it's very hard to actually write an algorithm that does the job, and it also like gives you visual output, at least here in C#, because otherwise so let me continue, and perhaps once we're done we can add more visual flavor to this. Okay. So how are we going to continue? Now we need to merge them together. Okay, so I'm going to do it in a bad way so that it gives me an error, and then I'm going to explain why. And now the last step. The last step is we have split the polyline in two. Each one of those two gets simplified down the tree recursively. But then, assuming these two branches of the polyline have been simplified, we need to reunite them somehow and then return them as part of this function. So we need to take the left part that has been simplified and the right part that has been simplified, put them together as a list again, and then that will become the simplified polyline. So that's actually fairly easy to do. So what we can do is we can say the clean points, I'm going to remove this now. The clean points list that we want is going to start with the points that have been simplified on the left part. So left simplified, okay? And after that, I'm going to take that polyline, that list, and I'm going to add a range of elements right after it, which is going to be all the elements that have been simplified. You can see that I am getting here I'm starting to get some results. So you can see here that the distance to the lines is actually quite small. And as I keep going smaller, you can see that this one doesn't simplify anymore, and this one, and this one. So it's kind of working, all right? You see it working. and here, bam, no simplification whatsoever. However, it's not great, it's not perfect. And if you have a sharp eye on this one, you can see that we're running into a problem here, and the polyline component is actually complaining. You see, zero line segments were collapsed to create a valid polyline. What this means is that if you look at the list of vertices, we're actually outputting a lot of duplicate vertices. What that means is that vertex number 2, this one, is duplicate, vertex number 3 is duplicate, and number 5 is also duplicate. Why is this happen? Well, if you remember, what we just did was, I'm going to take this segment here and I'm going to simplify it. And imagine that it simplifies completely. Like, imagine that it simplifies like in this scenario here, all right? Where all the points on both ends are absolutely simplified. So I'm only left with point 0 and point 2. And imagine that all this stuff also gets absolutely simplified and I'm only left with vertex 2 and vertex 6. What happens is that here, imagine they all get absolutely simplified. The left simplification has vertex number 0 and vertex number 2, but the right simplification has also vertex number 2 and vertex number 7. You see where the problem is? We are duplicating this vertex on both ends because of this duplicity that because we sent this vertex to both ends of the subdivision. So the only thing that we need to do here is we need to operate a little bit with this right simplified, and then make sure that we do not add here to clean points, we do not add the first vertex of this end. So that is just as simple as saying, for example, avoid duplicating split point. And here what I'm going to say is like, for right simplified, for the points that are coming from the right, for example, I'm going to remove the one that is at position number 0. And as I do that, I can hit here, okay, and then you guys can see that now I am still getting the same result, but I am not getting duplicates. Is that correct? I'm not getting duplicates, I'm not getting any duplicate, I cannot see any duplicates here, and then as I go, pop, 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 simplification, yay! Woohoo! All right, this worked. I can't believe this worked. And it only took us an hour and 15 minutes. That's not terrible. Okay, before we wrap up, let's get fancy and let's try doing this with a nicer example. So let me rewrite something here. Okay, so let's get a little fancy here. Okay, so I'm going to draw that kind of curve that we saw. Okay. Okay. So I'm going to take the curve, I'm going to pull it in here, and then I'm going to subdivide this curve. Divide curve. I'm going to subdivide it in, for example, 100 elements. Okay, and then I'm going to plug that in there and see if that works. Okay. an algorithm can do. So complex NURBS curve here on Rhino. I have brought it inside of Grasshopper, and I'm going to subdivide this, for example, in 100. Let me do 200. I'm going to subdivide this in 200 vertices. You see there's I'm going to plug this into the component that I just created, the list of points. And because it's 0, right now it's not simplifying at all. But you can see that as I start opening this up, you can see how the polyline starts simplifying a lot very fast, you see, and then that one simplifies, and this one simplifies, and the other one simplifies, all the way until I can probably yeah, so let me, okay, and this is a better way of looking at it. So you can see how super cool the vertices on the curve are maintained, because those are the ones that are giving the curve a lot of detail, whereas on the segments that are almost straight lines, then all the vertices are removed. So how awesome is this algorithm, huh? So let me do that again. You see, with a very low value, 0.3, you can see that it's these parts that get oversimplified, but the parts that have a lot of detail stay in. So, and then let me crank this up a little bit. And then here, and then, and then okay, simplification up and simplification, yay, woohoo! All right, folks, this was the Douglas Peucker, blah, 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 I always forget the name, sorry, the polyline simplification algorithm. What I would like to finish saying is this implementation that we just did today is not at all the most optimal or the fastest or any sort of thing of that kind. There are other algorithms, there are other ways of implementing the same algorithm that actually do a much better job by using some simplifications. So for example, recursion is a method that is very easy to use, and a lot of people consider it very elegant. But depending on where you are working, and depending on how many elements or how many consecutive calls to a function you do, you may actually hit a limit. There are certain programming environments where you can only do recursion at like a fixed number of depths. So you cannot call a function itself more than, for example, 32 times. So this is not the case here, but it might happen that you might be working on an environment where you only have limited recursion. So there are other ways of implementing this algorithm that don't really use recursion, that they use infinite loops, while loops, until they have all the situation figured out. Also, we did calculate the Euclidean distance between each one of these points and the line. When you're doing distance calculations only because you want to compare those distances between other distances, then it's much more optimal to do what's called the squared distance, which is basically the calculating the distance but without doing the square root. The square root is somehow a heavier mathematical computation. So if you can save yourself doing square roots, it's usually a better idea. And in this case, we could have done that because we don't really need the real value. We only need to compare those values against each other. And the two values one will be greater than the other. If one value is greater than the other, the square of those two values will also be greater than the other. So that could have been a simplification. And also, something that we did is that we did compute the linear distance between the point and the line. But if the point had been here, for example, we would have still calculated the distance to this line. Whereas I believe the real algorithm, what it does is that it computes the shortest distance of that point to the segment, which is a slightly different operation. But for the sake of illustration and for the educational purpose, which was what I want to do here, this was an algorithm that I thought was easy enough to implement and break down its logic. So I hope you had fun, and if you like this kind of tutorials, please remember to subscribe, to hit the notification button, and to learn more about geometry operations and geometry gems. Thank you very much. All right, so I think we're almost ready to go. So what I'm going to do now is I'm going to record the introduction, as I usually do, and then I'm going to record the introduction, and then I'm gonna spend like 5 or 10 minutes doing some Q&A with you. So let me see. Do I want to go back here for? Do I want to go back here for the intro at all? This is not really saying anything. I can just explain the algorithm by being here and scrolling, right? I'm going to hide this, and if I hide this, now it's easier to see how this polyline simplifies, right? Yeah, it's much easier. Okay. Okay. Okay, so let's do this. I'm going to zoom in here. I'm going to zoom in here. I just don't want all the spaghetti to show up. To show up here. Yeah, I got out of the way. Okay. So what am I going to say? I'm going to say that this is the polyline simplification algorithm, that we're going to rely on some code. No, that I already said in the video, so I'm not going to say that. I'm going to do a disclaimer that it's not the most optimal way to do it, but it's a good way, one to learn. And I also want to say that it's going to be implemented in C# with C# scripting in Grasshopper, but that it's not going to use any of Rhino commons. So this can be ported to any other. This code can be ported to any other C# based environment very easily. Okay, so let's do that. Hello, and welcome to a new geometry gem. On this gem, what we're going to do is we're going to implement a polyline simplification algorithm. It's called the Raymer-Douglas-Peucker algorithm. And let me show you how it's going to look. I have here a polyline. I have a curve that I have subdivided in 200 elements. So I have a polyline that has a lot of tiny, tiny elements between vertices that are very close to each other. But with this algorithm, I can set a threshold distance that I'm going to use to define which vertices are not really giving me any information or any meaningful detail for this polyline and which ones are important for the overall shape. So as I make that distance a bit larger, you can see that the polyline starts simplifying, but altogether, overall, it kind of keeps the overall spirit of the general shape. So this algorithm is really good for simplifying points that are not really adding a lot of detail or that are like almost like tangent to the polyline at certain times. So you can see how detail starts popping up on the curves, on the curvature, as opposed to the more straight line segments, you know? So this is a super, super useful algorithm to simplify, for example, drawing strokes or to simplify trajectories for drones or for robots. And it's also a very nice one to implement just geometrically. It's also very easy to implement conceptually. And actually, full disclaimer, this implementation that we're going to see here is not at all one of the most performative or one of the fastest ones. But I believe it's one of the ones that is easier to understand, so it has educational value. But if you're looking for a performance implementation, then perhaps this is not where you're going to, where you want to look. You want to look for an algorithm to learn exactly how this works. I'm going to be implementing this in Grasshopper for Rhino, which is a parametric modeling environment connected to a 3D modeling environment that allows me to do C# scripting. I'm going to use this environment because it gives me a lot of visualization capacities out of the blue, with very little effort. And as you can see, you will see that in this code, I'm almost not using any of the libraries that come with Grasshopper. So you will be able to take this code and replicate it in any other C# based environment, like for example, Unity, VVV, or Mac, you name it. Okay, so follow me and let's get busy and let's implement some cool simplification algorithms. All right, choo-choo, we're done. Ah. Okay. I was recording this, right? Oh, yes. Okay. All right, wonderful. Thanks everybody for sticking around. I will post, as usual, I will post the files and the videos once we get them edited, and they will only go here. They will only go on this channel, parametric design, parametric camp. Sorry. And I'm gonna open it up a little bit to Q&A. So I'm gonna look at the chat. Andres is asking to see the code again. Well, I'm gonna post it right away on our GitHub page. So after our friends help us clean it up a little bit and make it more decent, like Hari Prasad, who's just writing on the chat, has been helping a lot on that front. But also the video stays online immediately, so you can go back like now and just look at the video again. Audio failure, I don't know what's happening with that, sorry. Probably first 30 seconds with audio problems in this curvy one. Well, you guys think it's cool. I think it's very cool too. What can I say? I just really like writing code that generates geometry. It's one of my favorite things in the world. It would be nice to see how to retopologize overlapped curves. Can you expand on that, Galiev? On the next Grasshopper shop, would you be able to see some GUI-based plugins, also as the merge tool? Well, that is a really good point. The thing is, a lot of vanilla Grasshopper components, they allow you to play with the UI. They allow you to play with the component and add more inputs, add more outputs. They have some of them have this banner that pops up underneath. But the thing is that a lot of that, doing that in C# script components is very tedious, and some of those capacities are actually not available. So a lot of that functionality is only really available if you're writing the component from scratch. So if you're developing Grasshopper plugins, which is a topic that I really want to get into, and I will get at some point, how to write your Grasshopper plugins from scratch. But we're not going to get into that, at least yet. I want to cover, before we get there, I want to cover more basic stuff, and I want to build up more basic playlists so that everybody gets up to speed, and then people who join the channel have a repository of the basics that they can learn to catch up with the level of the things that we will be doing in the future. Can you slowly introduce more complex algorithm? Is super cool. Well, that's kind of what we did today, but there's a lot of these things. There's a lot of these kind of algorithms out there. So the more I find them, the more I'll just bring them. And that's a little bit of the spirit behind the geometry gems. Just like honing on one particular algorithm that does some functionality, and then just breaking it down, you know. Um, that was fun. That was great. Thank you. I like the idea of implementing geometry algorithms. We're going to do a lot of that here. So don't worry. There's going to be a lot of that, Rafael. um, okay. Thank you, Hex. Thank you, Sujai. How can we review and find if one algorithm is more optimized? Ooh, that's a good question. So look at this. Let me see if there's like is there simplify curve? Let's see if we can. So for example, this one, optional deviation tolerance and angle tolerance. So let's see if, actually, oh, sorry, you're not seeing my screen. Yes. So let's see if, for example, this is a polyline curve. This one is also a polyline curve. So let's see if we plot both of them, if we get the same simplification. Am I getting? So interesting. So you guys can see that the simplified curve in Grasshopper probably is using the Douglas-Peucker algorithm as well, because I just plugged in this one here, and it's this value, and it's giving me the same simplification. So that's interesting, but it's also using an angle tolerance. So maybe there is another simplification algorithm out there that we can use for angles. I'll do some research. But the thing is, you can see how as I do this, so let's say I were to subdivide this in, for example, like 1,000 points. Okay, that's going to take some more time. So you see, my component is taking 16 milliseconds to compute that simplification, whereas this one is so low that it's not even showing up how many milliseconds it takes. So usually a way to measure optimization is computation time. It's mostly computation time, actually, I would say. So this one is much faster. Also, this component is compiled. When you compile components, they're also much faster. But that's a different story. But you can see that, you see, when it's 0, mine took almost 30 milliseconds, whereas this one took 7 milliseconds. So this one is much more optimized. Next level of this algorithm can be surface panelization. It could be, yeah. So we can take a surface, we can panelize it in the 2 directions, and we can apply Douglas-Peucker to each one of those directions, and then reunite that surface as panels. That is true. There's probably like stuff that we would need to break down there, but that is an interesting topic. Is this somehow the way Rhino calculates the length of nerves curves? So yeah, Rodolfo. Rodolfo is you're right. Very often nerves curves, because they are defined by functions. If you were to compute the real length of those curves, you would need to do calculus. You would need to apply differential. You would need to do derivatives, and you would need to apply integrals to calculate the length of those curves. And that's something that computers have a really hard time doing. So very often, in order to calculate lengths of nerves objects, what you do is you basically subdivide that object into a lot of points that are very close to each other, and you calculate the individual lengths between them. It's an approximation. It's not really a real value, but very often it's good enough if you have enough sample points. That's a good one, Rodolfo. Display is always an approximation. Also, same thing, Rafael, you're right. A nerve's surface cannot really be represented exactly. So internally, Rhino, what it does is it subdivides it in a mesh that has like a lot of triangles, and it gives you the impression of smoothness, but it's really, really just a subdivision of because GPUs, graphic cards, can only take triangles. They cannot operate with continuous geometry such as nerves. What is going to be my next topic? I have no idea. Kartik, what would you guys like to see? I've been meaning to start. I've been meaning to start an intro to Grasshopper series because I use Grasshopper a lot in my teaching. So I want to record like a let's do Grasshopper and like what is the interface points, blah blah blah, whatever, and then perhaps get into more complex native Grasshopper topics, such as, for example, data trees and data manipulation, and do like a lot of examples. And we hopefully, when that is done, I can move on to let's start learning C sharp. Because I've done a lot of C sharp with you guys, but I haven't really gone into the basics. So, and that's also something that I will need a lot for my teaching. So I want to get into those, but I'm not going to. I don't think I'm just gonna start just doing only that. I would like to keep doing some of these geometry gems, maybe go back to the algorithmic modeling challenges. So I'm always open to suggestions. So if you guys wanna suggest something, I don't really know what I'm gonna do next week. So, and also I'm going to be working full time this summer, so I may actually have to change the streams from Fridays to Saturdays because I will be working on Fridays. So, I mean, what I have a full time job now. I teach in at the GSD here at Harvard, but I'm during the summer I'm going to be doing a different job that requires me to be in the office like 9 to 5. Um, Galiev retopologizing some. Imagine that there are three lines which lay on each other. In the end, we need a single 10 centimeter line. So overlapping. So you mean overlapping elements? Well, we could take a look at that. Jose, could you give us tips about selling services online using Grasshopper? Like talking about online services, hosting, geometry usage, some kind of guidance. Are you talking about selling your services, Fernando? Are you talking about selling your services as a consultant online, or making a Grasshopper script and putting it online and then charging people for using it? What are you thinking, Fernando? Rafael is asking for the Discord channel. Yeah, I know. I have it. I have the server. I have everything. It's just that I really don't have time to take care of that and setting it up. If anybody wants to volunteer and help me with that, we could speed up that process. But as of right now, I honestly have a lot. Like just taking care of this and putting this together and the videos and the files takes a lot of time. So I really don't have time for like any more chatting or like moderating a Discord channel. But if anybody wants to help with that and become like the community manager of this Discord channel, I'll be more than happy to talk about that. Hex, data trees, and data manipulation is a good series. Yep, I know, and that will be probably like the last part of this intro to Grasshopper series that I want to do. Grasshopper item picker of Heteroptera plugin. I don't know the Heteroptera plugin. I may need to take a look at that. And can we have a class of an active design? Thank you, Luigi. We just wrapped up that semester on 2 days ago on Wednesday. I also I can probably share some of the work or like talk about or do some examples of the work that I did there. I have a workshop. We did a workshop one day in class that was about connecting Grasshopper and connecting processing to runway ML to do machine learning and then communicate back and forth. I have that link. Where is that link? That I think that's in my personal YouTube channel. Oh, okay. This one here. So if you're interested in, and this was a workshop that we did in class in active design. So if you're interested in that, I'm gonna paste there a link, and you can check it out. But we can also cover like more topics related to that. Sure. And also a class about graph clustering, Ernesto. Ooh, that's quite something, graph clustering. But yeah, we could take a look at that. What about basic Grasshopper? Are you guys super pros? You don't have a problem with that? Um, okay, and then I'm just gonna wrap it here. Okay, I'm going to save this. Okay, for example, there are several processes in the architecture that can be automated, for example, using coding in Grasshopper. Everything we learn here with the material can be of practical use to solve real problems on a daily basis. Of course, Fernando, that's hopefully my goal. That things that you learn here can be used and can be applied in your real life world and can help you automate a lot of architectural processes. Said is asking for processing in P5.js exercises. That is a great idea, but I honestly think that Dan Schiffman is doing such a great job, and he has so much stuff on that front that I'm not eager to start doing any of those anytime soon, and I would like to perhaps focus on other platforms that he doesn't really cover that much. I would like to focus more on computational geometry, which he only touches when it comes to 2D shapes, but I think we can do a bit more of like 3D form generation here in this channel. And and I also want to touch other frameworks that he doesn't really do much. For example, we're going to be using a lot of Grasshopper here. We may start using Unity. We may start using VVVV, even Touch Designer. Why not? And and but but I'm not going to start doing processing or P5.js tutorials unless we're doing that because we are writing things that talk between processing and Grasshopper and P5 and interoperability and that kind of stuff. But he's so good at processing and P5 that I don't feel like I can contribute anything in that conversation. So if you want to learn P5 and processing, just go to the coding train. There's so much stuff there already. So just I think he does have a recent video about this thing that we just did to the Douglas Peucker algorithm. So you can also check that out. Okay, fractals. Oh, point clouds. Oh, yep. That is definitely topics that we can cover. Shaders. I want to do shaders. I'm so excited about shaders, and I want to do machine learning too. And robots. We need to do robots. I've done so much in the robotics field. I can tell a lot. I can share a lot of stuff when it comes to robotics. So well, one step at a time. Okay. So let's figure out the basics this summer and do like Grasshopper, basic Grasshopper, and basic C Sharp. And then once we got that under control, then we can move on to like more high level stuff. Okay. Um, but yes, exactly, Said. So I'm more than happy to do interoperability, and like I showed the other day this thing that I could draw in processing and then send that via WebSockets to Grasshopper, right? And actually, that example could have definitely used some simplification algorithms. That would have been like this one. That would have been great. Uh, a class showing how could we actually use coding as a job, mainly these times of Corona. Very honestly, Fernando and everybody who's listening to me right now, if you know how to code, you're gonna have the easiest time in your life finding a job, especially in these times of Corona, where working from home is becoming so important, and where there's so much need about writing digital environments that help us manage our new digital life. Um, Coding is like a super super great skill to have. We focus a lot on geometry generation on this particular channel, for example, in form finding and design. But if you want to do like database optimization, you're gonna get like really really high paying jobs. And also if you want to stay in the design art, architecture field, which is more a little bit of where I situate myself. There are many companies, many large architectural office, many design studios that more and more are understanding the power of coding and computation as a new tool. So if you start learning these things now, I'm very certain that you will have a much easier time finding a job as a computational designer, as a creative coder in the world that is coming. I see those jobs popping up more and more often. When I started in this field, there was nothing like that, but I see those jobs like more and more happening. So keep going and keep getting better and do cool stuff, and you will have a very easy time finding a job, I think. Uh, you want pro stuff? You're gonna regret those words, Galiaf. I'm gonna give you some serious pro stuff. Okay, all right. And I think I'm just gonna wrap it up here because I need to go. I need to do other stuff, and I have some students that need some help. So thank you very much for sticking around. I'll see you guys next week on Friday. Okay. Thank you. Bye bye.